Hi, this is Dr. Sheets. Hope you're having a good day. Today I'm going to talk about the relational database model. It's the most important development in database history of all time, and it's responsible for probably 95% of all databases in operation today. It's very, very important, but the beauty of it is it's also very simple. Everything is designed as a table where there are columns that describe the different data that go with each thing, and then there's a row with the data from that thing in the world, right? So that's what you have, rows and columns. And then we have a way to make what's called a relationship between two tables. And once you understand those basic ideas, the ideas that there are tables, and then there's a way to make relationships between tables, you basically have everything you need, and from there on it is learning more rather than new. Well, what we're going to talk about is the relational database model. It has built on the concept of relations, and as I said, a relation has a set of columns that describe the data that is to be kept for every entity or instance of the entity in the table, and then the rows represent the actual data. So the columns or attributes say what data need to be kept, and then the rows are the actual data from the thing in the world. And then once we build our system, design our system as relations, then we can pretty much create step-by-step process of converting our relations into tables within a DBMS like Access or Oracle or other relational database management system. Well, foreign keys are one of the most important concepts. That's how relationships are implemented. We have a primary key, which is a attribute that has a unique value for every row in the table. And then a foreign key is an attribute where we store values of primary keys so that we can relate a row of one table to a row in another table. And I'm sure you'll have all of this you can stand by the time we get a few more weeks into the semester. Well, the logical view of data is important because it used to be that we had to worry about putting things down on the disk. We had to know that what was the block size, how many records were going to fit into a block, and sometimes those little physical decisions would impact the actual attributes that you would have in your system, and that doesn't make a lot of sense, right? I mean, the system needs the data it needs. It doesn't need to be limited because of something to do with the block size or some physical way the data is going to lay on the disk. And that was the idea behind relational databases. Just separate that whole process out and be able to focus only on the data and not think about some of the complex things that you need to do to be able to put data actually down on the disk. And before we had DBMS, programming was much more difficult than it is today. Well, so the idea is this simplicity allows us to focus on having the right data to solve the problem, and solving the problem without thinking about how you're going to make an implementation is where this started, right? Trying to take the complexity of added by the physical characteristics and just allow you to focus on the data that you need to solve the problem. Well, the relation is the key idea, and so a relation is this set of columns that are attributes, and there's a set of rows that are values for attributes. So here we have a little example. We have this relation, we call it a table here, but we could just as easy call it a relation. And our relation, our table is student, and it has this set of columns where there's student number, student last name, student first name, student initial, student date of birth, student hour, student class, student GPA, student is a transfer, department code, student phone number, and professor number. So those are all attributes of the relation student, or columns of the relation student. And then here we have the data for Walter Oblonsky. And that data in the row are values for those attributes. So Walter's student number is 324269. His middle initial is H. His GPA is 309. So every one of these actual values comes from something in the world. And we just interrogate that thing. In this case, that thing is a human, so we can just ask it a question. What department are you in? And then they tell us our department code, and we can put it into our system. Right? So if this is a relation, this is our relation student. It consists of the columns, student number, last name, first name, initial, date of birth, hours, class, GPA, transfer or not, department code, phone number, and professor number. These are rows, also known as tuples. These are columns, also known as attributes. The important thing to remember is it's these attributes that are what we design. Right? We say these attributes describe a student. A student has a student number. A student has a student name. A student has a date of birth, which means that we can describe the generic student with these attributes. Then we go and get the specific values from an actual thing in the world, an actual human student, and then we put those values in the rows for those columns or attributes. Well, there's some definitions of what is a table. We always think of tables as this two-dimensional structure, rows and columns. The tuple or the row represents data from some single thing in the world. It's not data for all students. It's data for a student. Each column is an attribute. Has to have a name. Each row and column represents each row and column intersection. For example, right here can have only one value. Right? We have the row of Gerald Robertson and the column of student hours, and it can only have one value. In this case, it's 120. So the values of a particular column all have to be in the same format. The column has a specific range of values that are in that format. For example, the format might be a 2-byte string, and then the column had the attribute domain range are the 2-byte character abbreviations of the states. Right? So if we had a state code attribute, it would have a format of 2 characters, 2-byte string, and it would have then the attribute domain is the range of 2-character state codes. Whoops, sorry. The order of the columns doesn't matter to the DBMS. All tables must have a key. Whether that key is one attribute or some combination of attributes that uniquely identify every row in the table. And that is like really, really, really important. You can't overemphasize how important it is that each table must have a primary key. Well, what key means is that each row in the table is uniquely identified by the value of that attribute. So if we look here at student number, right, this attribute, this column student number, right? Every one of these student numbers is different from each other, right? So student number could be the key of this relation student, because what it means for a column to be a key, it means that every value for every row is different for that from every other value of every other row for that column. This value 324269 can never appear in another row in student numbers. There can only be one student number 324269, right? It must be unique. And that is the idea of primary key. It is some attribute that we've selected or designated to contain values that will always be unique across all rows of the relation. Well, the reason we have a key was for the purpose of finding all of our other attributes. Because if we know the key value, then we can instantly go to the right row in the table and then find all the other values for that particular student in our case. And that is the role of the key. The key determines the value of other attributes. So if you know the value of the key, then you can know the values of the other attributes. If you know the value of attribute A, you can determine the value of attribute B. Excuse me. And so that's this idea, right? If we know this key value, 324291, then we can find this row in the table, and then we know that for Gerald Robertson is where this data all came from, and that's what it means for determination, because all we need to know to be able to find all that data is the value of the key. That's the only thing we need, because if we know that, then we can find the row with all the other data values that have come from Gerald Robertson. Functional dependence is sort of just a fancy way to say determined. Attribute B is determined by A. Attribute B is functionally dependent on A if all rows in the table have the same value for A, also have the same value for B. So now that is sort of a more abstract general definition, right? But for in terms of what we want to remember is that we want our attribute, our key, to functionally determine every other non-key attribute. So all non-key attributes need to be functionally dependent upon the key. And in a couple of weeks, when we get to normalization, we'll have a mantra that we say about keys and functional dependence. And it is the idea that every non-key attribute must be dependent upon the key, the whole key, and nothing but the key. Every non-key attribute. You get it. Just keep saying that until you meditate some. Right? So functional dependence is this idea that if we know the value of one attribute, we can find the value of other attributes. And so in our world, what that means is if we know the value of the key, then we can find all of the other values that have come from the entity in the world that is identified by that key value. Well, there's several types of keys. Composite key means that we've combined attributes. And remember, the reason we have keys is so that we can uniquely identify each row in our table. And that is the true key idea. Well, so a composite key is a key that combines two or more attributes to achieve uniqueness. A key attribute is any attribute that is part of any key. A super key is a key that contains, a super key is any key that can uniquely identify each row. A candidate key is a super key without any unnecessary attributes. And I don't even like to have make big distinction there, because, if it's a super key that has more than the minimum attributes, it's useless anyway. It's not even worth knowing about or thinking about. It's just a confusing thing. So candidate to be key is the idea that I think you should remember, and that is any set of attributes that are, or any minimum set of attributes that uniquely identify all rows in the relation. Well, this is the most important concept in relational database, because all relationships in all relational databases are made through foreign keys, right? So the foreign key is the idea that we're going to have an attribute, and we're going to have that attribute in our relation, and that attribute is going to contain primary key values, right? Primary key values, values that identify a particular instance in some other relation, a foreign relation, right? So we're going to create a new attribute in our relation, and in that attribute we're going to store primary key values of some other relation. Excuse me. And we're going to do that so that we can associate the row in our table with the row in the other table, the foreign table, identified by the value of the primary key that we have stored with the row in our table. And through foreign keys is how all relationships in all relational databases are implemented, with the simple idea of a primary key, and how that primary key has values that uniquely identify every row in that table. And then the idea of a foreign key, which is an attribute that stores those primary key values so that we can associate the instance in our table to the matching instance identified by the primary key that we've stored as a foreign key, and find the data that matches our data. Right, so what we do is we store the foreign key in one relation, and that allows you to find the unique matching tuple or row for that key in the other relation. See if we can have a look here. All right, so here we are. We have two relations, product and vendor. Product has attributes product code, product description, product price, product on hand, and vendor code. Now you can see all these things describe a product, right? Because the vendor that created a product is a valid thing to know. So these attributes all describe a product. But there's a whole bunch of vendor data stored in our vendor relation, like the vendor contact information, the vendor area code, and the vendor phone, right? That if we stored it with the product, it would be redundant, right? Because here you see we have 232 and 232, so what we are if we stored these things for 232, we would end up storing them multiple times, and we hate to do that in our database, right? We only want to store each fact one time, right? So we only want to store the fact that Annalise Crystal is in area code 608 and has phone number 224-2134. We only want to store that value once. And I said here, if we put them up here with the vendor code, right? We could just store that stuff multiple times, but that would be bad. So what we do is we have this attribute here, vendor code. And vendor code is a foreign key to the vendor relation. And the primary key of the vendor relation is the vendor code. So what we're going to do in our foreign key is we're going to store values of the primary key in vendor of vendor code as attribute values for each of our rows in product, so that we can then say which products was made by each vendor. Right? So now let's take a look at this for a second. So here we see that a claw hammer was made by vendor code 232. All right, and the house light chainsaw 16-inch bar was made by Henry Ortozzo, or the vendor code 235, and the contact information, the contact is Henry Ortozzo. Sledgehammer was made by come on, there we go. All right, 232. And 235. Whoops, almost blew it, didn't I? All right, so what you're seeing here is you're seeing that we have one instance. For every one instance of product, we identify one instance of vendor code. Right, and here's 232 is associated with 232. Right, so the reason that we store the value of the primary key from vendor code in vendor as a foreign key vendor code in product is so that we have the value of the primary key here in product, and then once we have that value and we know it has the characteristic of being unique across all rows of vendor, we know for sure that we can find the one vendor that supplied that product. And that is the concept of key and foreign key. We create this link logically, or there's no actual string or anything, right? We create that link by storing the value of the primary key as a as part of the row in the foreign key. And I think foreign key is a name that makes sense, because what you're sort of getting is a key value for a foreign entity or a foreign relation, a different relation. Either way, it doesn't matter that much. You just have to memorize it. This is the key concept of relational database. This is what makes it all work. Right? So you see the idea how each foreign key, the foreign key value attribute, vend code, contains a value that identifies one row in vendor. Because why is it one row? Because each value uniquely identifies a single row. And we store that primary key value in the vendor code. That way, we can easily find the right vendor information. Now, I want to bring up one other thing while we're here. Right here, we have one instance of vendor is related to two instances of product. And I think that makes sense. One vendor can supply many products. But this is a one-to-many relationship where one instance of vendor is associated with many instances of product. And one instance of product is associated with one and only one instance of vendor. Why is it one and only one? Excuse me, it's one and only one because there can only be one value of the primary key stored for each row for the vendor code. And that's why the idea of uniqueness and the idea of a key is so important. So that once we store these primary key values as foreign keys, we're guaranteed to be able to find that same row that was in that table prior to storing it here. Well, an entity has to have integrity. The idea is really you must have a primary key. Every entity must have a key, or every relation. As we go through here, there's some jumping back and forth in terminology between entities, tables, and relations. They're really all the same thing, right? An entity, a relation is the same thing as a table, which is the same thing as an entity. Now, and so each row is what I like to call an instance. And I say it's an instance of an entity because it makes sense. It's easier for me to think of these entities in the world out there running around, right? So I guess student is the perfect entity. So I have these students, and then I have these attributes that describe the students, and then I have a row for each student. And that row is an instance of the entity student because it contains values provided by a student. Well, nulls are a special condition. Generally, you should never use anything that can be null. No attributes that can be null as any part of any key. That is a rule. It can never happen. Should never happen. Now, none of the DBMSs actually prevent you from doing these things. So if you're insistent, you can still do it wrong. If you have an attribute with a lot of nulls, you should reconsider your design, because it's rare that you actually have that situation where you've designed a relation, and most of the time, for most of the rows, one of your attributes doesn't have a value. That's what null means, no value. And so that's usually not a really positive design. Well, determination goes along with the concept of functional dependency. We touched on it just a minute ago. But what we want to know, to be guaranteed in our database, that when we know the value of the key, we can find all of the other values of the other attributes that we need. And the need for determination is why we have keys. And once you have the primary key, that enables the whole idea of the foreign key, right? Because we just saw there that we're storing only one value. And that one value is a primary key value that identifies an instance in another table and so it relates the data from the instance where the foreign key exists. It relates that row of that table to a row in another table that is identified by that primary key value that was stored as the foreign key value in the first relation. And the reason it works is that we have a key, right? And we know that key is going to identify all the other attributes, the data for all those attributes, because all those things, not only the key value, but all the other attribute values, have come from the same thing in the world, right? So they've come from the same student. When we get a student ID from someone, that student ID is unique across all student IDs. So that then when we have the other information for those people, we know that we can always find it by knowing that key value. Well, functional dependency is this idea taken into like a little bit more formal representation. So functional dependence means the value of one or more attributes determines the value of one or more other attributes. The determinant is those attributes whose values are determined and are doing the determining, right? So those for us are the key values, and the dependent are those values who are going to be determined, and those are the non-key values. And what we're looking for, and you'll learn a lot about this in the normalization chapter, is full functional dependence, which is the means the dependent attribute is determined by the entire collection of attributes in the determinant. And that just means that you need all the multiple attributes of a composite key to make uniqueness across all rows, and it's that uniqueness that then determines the other attributes that you are needing. So here's my example for this, and remember, we're thinking about functional dependency, and the idea is that we want to know what attributes functionally determine the quantity purchased. Right? So if I ask you to say, well, what is the quantity purchased? I guess you could give me some numbers, right? But if you said, okay, I'm adding up all the quantities, so I have 2, 1, and 5 is 8, 4 is 12, 16, 26, 27, 28, 36 is the quantity. Well, that would be wrong. Right? If you pick out just one of those quantities, like the quantity is 1, how would I know if you were talking about order number 901, item number 20, or order number 903, item number 10? Right? Functional dependency means what attribute values do you need to know to find the attribute values that you want. Right? So the attribute values that we want are quantity. So what do you need to know the right quantity? What do you need to know to tell me one value? If I ask you the question, what is the quantity purchased? You need to know 2 things from me. Those 2 things are an order number and an item number. If you know the order number and item number, you can know the quantity is 5. Otherwise, you can't answer the question, because it's order number and item number that determine how many of a particular product are purchased on a particular order. This is the simple idea of functional dependency. You had to know 2 things. You had to know both the order ID and the item before you could know the correct value of quantity. And I think this is a good way to think about functional dependence, because without those 2 things, you couldn't know, right? If I just give you the item number is 20, right? Then you have 2 different values to pick from. Is it 2 or 1? Right? But if I tell you then after that the order number is 903, you instantly find the right one. And so quantity is functionally dependent on both item number and order number. Well, some of these definitional things I'm not so worried about. The entity integrity, we maintain that by making sure that every entity has a primary key and that no part of the key can be null. We're guaranteed to be unique across all invoices. An example is that invoice can never be a duplicate, right? As you put out a new invoice, it's just an increment. So there'll never be a time where we have another invoice that has the same number. Referential integrity is a little more interesting. There we are looking at the idea that once we've used a primary key value as a foreign key value, once we've taken the key of vendor and stored it as a foreign key in product, right? We say that now the foreign key in product refers to the instance of the vendor identified by vendor code 235. Right? So that's how we are thinking about our referential integrity. So that idea is once you've done that, once you've used the primary key as a foreign key value, then you should never be able to delete that row in that table where there was the primary key. Because if you did, then the foreign key would have a value that points to where there's supposed to be a row, but there would be no row. You would have lost referential integrity. And so that is the idea of referential integrity. Well, so if we think about that idea, so here we have an agent code, and where agent code is the primary key. And so we can see there one instance of agent, agent 502 is associated with 1, 2, 3, 4 instances of customer. But each instance of customer is associated with only one instance of agent. Right? And that's because this is a one-to-many relationship. One agent handles many customers. One instance of agent is related to many instances of customer. And they are related by storing the value of the primary key of agent as a foreign key agent code in customer. Right? So for every instance of customer, we know the agent that manages that customer. Well, relational algebra is a sort of a more abstract way of thinking about database problems. Now, it is also built on set theory. So you already have knowledge of this thinking. Now, I think when I was in school, we learned set theory in 8th grade. Someone told me the other day it was pushed down now till 3rd or 4th grade. Right? So you've been aware of these ideas for a long time. And so this relational algebra was developed at the same time the relational model was, and there's a bunch of professors that put it together, really just a couple, and they like thinking about these kind of things, and they like designing these ideas. Now this is the basis for SQL. Like everything that you do in relational algebra has a corresponding thing in SQL, so it's also highly practical. Well, so we have relational variables that are that can contain relations. And one of the things about this approach, and we do a lot on relational algebra in 5524, at least we have been over the years, because relational algebra gives you a way to optimize your queries using a series of properties and axioms and to transform one query into another equivalent but more efficient query. Well, what we do as we are designing our system is what we're really sort of doing is recording or creating our functional dependencies. And when we create a set of functional dependencies, there's always another set of implied functional dependencies that go along with those ones that we have explicitly created. And the closure is this idea that we can use relational algebra to make sure we know of all the functional dependencies that are in our system. Even if we haven't designed them specifically in our system, we can apply this algorithm and these techniques to make sure that we are aware of all of the functional dependencies that might exist. Well, so we have a set of operators, and they are ideas that you've seen before, especially probably things like the union between two sets and intersection between two sets. Those are ideas I hope that when you hear them, you say, oh yeah, I remember that. I remember that the union of two sets is all the things in both sets. And I remember the intersection of two sets are the members of the set that are the same in the two sets. And so you already know a lot of this stuff. It's just now trying to formalize how you think about those things. Well, select is our first operation, and all select means is to limit the number of rows that should be returned as a result of the query. So here we start out by selecting all, and of course that gives us the exact same query. But if we make a condition, we'll say where price is less than $2, right? What should we get? We should get 2. We should get 9-volt battery and a 100-watt bulb, and that's what we get. We have selected, based on this condition, price less than $2, and then we use that rule, that conditional, to pick out the ones based on the price column. And here we see the power of key, where we have given we know this P code, right? So what we do is we select for the row that has that one P code. Since we know it is the key, we know there will only be one value. And that's select. Select just means limit the number of rows that are returned. Project just means limit the number of columns that are returned. If we project price, we just get a new table with one column. Description and price, we get 2 columns. P code and price, P code and price. Project means limit the number of columns. Well, union is different from select and project because it requires 2 tables. And the tables have to be what's called union compatible, which means their data types have to be the same. Now, they in this case, the data types are the same, and here this is an integer, this is a string, this is a 2-bit dollar. Here we have the same thing, an integer, a string, and a dollar. So we can union these 2 tables. They are what's known as union compatible. And when we union, what we do is we get all the rows from both tables. And here you'll see that since the box fan is in there twice, it's actually squeezed out, and we don't see it there. We only see one row for box fan. But that is the union. Show me all the rows that are in both or all the rows that are in either table. Well, the intersection is show me all the rows that are in both tables. All right, so we have, again, two union compatible tables where you both have a string in one and a string in two. That's really all you know, right? Employee name, first name is a string. Employee last name is a string. Student first name is a string. Student last name is a string. So there's all strings, so they are union compatible. But if we're looking at the intersection, there what we're saying is show me which members are in both sets. Which members of the set are in both sets? And of course we really only have one. Whoops, I got the wrong one. Franklin Johnson is the only one that is in both, so he is the intersection. Well, there's another set of operators that you can use, and we'll go into these in great detail in 5524. But most important by far is a join, and what we are doing, our strategy for designing the perfect database, is to create this key, foreign key structure so that we can then use it to create joins and get our data in and out in a really organized way. Well, the difference, as it might sound, is subtract table 2 from table 1, and what that means is show any rows that are in table 1 and in table 2 should be subtracted out. And of course we have our same situation where our difference is Frank Johnson is in both of them, so the final set is those that are those without Frank. And the difference again applies to the members of the set or the rows. All right, so now here we have an example of a Cartesian product. And what that means is we're going to take every row of product and combine it with every row of store, or whatever this whatever that table is. And then we're going to do that for every row. Good enough, right? So you see what we're getting? We're getting those 3 rows for every instance of product. Very rare that you do this. You might do it sometimes if you have really small tables, but it's not something that makes a lot of sense. Divide is something I've never used in real life. What it does is it takes the divisor, divides it into the one, it's a one column to one column thing, divides it in and tries to find where any of the values are the same. And here in this case there is one, so it returns just one row. Well, joins are really important. That's if it wasn't for the ease of joining, we wouldn't be able to make this key, foreign key stuff work very easily. And so it's the key idea. It's something that makes so much sense, though I don't think it should be very difficult to understand, because remember, the reason that what we're joining on, we're joining where the primary key value 99% of the time we're joining where the primary key value equals the foreign key value. Right? Because that's what we want to do. We want to find the matching data for this instance, which is in this other instance. Right? So most of the time we are doing an equal join, right? Where we are looking to say where the value in the primary key column is equal to the value in the foreign key column. And that's the most common thing that we do, are equal joins. Now we also, next would be a theta join. You'll never do a natural join, because you'll never have the situation where you ever have attributes that have the same names in two tables. That's just very poor design. And maybe it is have a name, natural join, but it's not very smart to not explicitly express all of your join criteria. So don't use natural joins in our class, meaning that you don't specify what the column names are and stuff like that. Well, an inner join is also the 90% case, where we are looking to return rows from two tables that are being joined on the equality condition, right? We're saying join this row in this table to this row in that table when the two values of their attributes are the same. And you can see where that makes sense. You have table 1, table 2. You're going to join where the primary key in table 1 is a foreign key in table 2. And so you know that there should only be the situation where there's some places where there could be a left outer join, where you have all the rows from the first table that has the primary key, and some of the rows from the second table where it's the foreign key. Actually, that should never happen either, right? If you have two tables, one table, the foreign key should never be allowed to be null, right? Otherwise, you are inserting a row without the necessary information. But anyhow, inner join is what we do the most of. Outer join just means give me all the rows that match from one table, and if there is no match, don't show for the other table. And so here's a couple little examples. Here's our two tables, customer and agent, that we are going to use to do a couple quick examples here. So it's customer and agent. Customer code is the key. Agent code is the key. Agent code here is a foreign key. So here we are. We're doing a natural join, and they're trying to give you the idea that things happen by step that are out of your sight, right? You just would ask for a natural join between customer and agent, right? And so the first step in that join is to create this Cartesian product, right? See what we're doing here? This is the same kind of all rows with each row with all rows kind of thing. And so that's the first step. Essentially, you made the product. You multiplied the two tables together, and you generated all these rows. Now you're going to come along and select from those rows where the customer agent equals the agent code, where the key equals the foreign key, right? This is the foreign key. The foreign key is in customer, and this is the primary key, which is an agent. Now you select, right, which means you pick out rows, and the condition is where those two attributes are equal. And then finally, you project off of that the different attributes that you want to see, and basically they just dropped one of the agent codes. And of course, the project, right, which we talked a little bit ago, means just pick off certain columns. And select means pick off certain rows. And this isn't that bad of an example, but this product, this Cartesian product, actually never be generated. The system can handle that without thinking about it. So here, a left outer join, that means we got all the rows from customer, but they're all the rows from customer, left outer join. But if there's not a matching row in agent, that's fine. Just let it go. So you can see here we have one customer, Smithson, who doesn't have an agent. Now, where does that agent code come from? Since you see an agent code, right? It has to come from where? Customer. Right? No phone number, because that only comes from agent. Here, a right outer join would be where you get all the rows for agent, and then if there's an agent that doesn't have any customers, you're able to identify that. And here we can see that agent 333 had no customers. So let's just jump back up here and look at our data here once before, right? So we have on the left outer join, that means all of the rows from customer and only the matching rows from agent, right? Right? So we end up with 421, right? There is no 421. So with the left outer join, we get this row, which we saw down there. And then in a right outer join, we get this row because there's no matching customer for it. And let's look and see what happens to Smithson down in that right outer join. You can see here Smithson in the left outer join, where the driving table was the customer, Smithson appears. But in the right outer join, where you get all of the agents but not any customers that don't match, here Smithson is missing. All because of whether there's an instance in agent, or whether there is a missing instance in agent, or a missing instance in customer. Well, the data dictionary and the system catalog are really important for keeping track of all of our systems, keeping track of all of our data, and this is a really important task. It's a way that we maintain everything we know about every attribute of every table in our system. And the system catalog is actually used by the system to find the attributes that are in a particular table and to find indexes and things like that. One thing is metadata, right, which is data about data. And that is, in the data dictionary, is where we describe all that, where we say what is the data type of this thing, what is the range of possible values that it can take on, things like that, for every attribute in the system. Is the attribute of foreign key? Is the attribute the key? What are the keys for the tables? Kind of things like that. Well, so here's an example. Here we have a little bit of a data dictionary, and here's the customer code. We get the attribute name, a slight description of what's in there. What is the data type? The format, what's the allowable range of numbers, is it required, is it the primary key or not, so here we are is our foreign key of agent code. These two things, right, should obviously be dropped down to right here, right? So agent code is a foreign key. Is it required? Yes. like that. And so this is just sort of the ideas. And wherever you go, you're going to have to do this kind of detail. And usually we do all this thinking in advance, right? Somebody actually sits down and says, well, what are the possible values that we're going to have for our customers? Then this how many customers we're going to have? Will this be a good enough range of numbers? And you think it through for every one of these choices, for every one of these attributes. And I want to say we had 175 tables in one of our databases, so these things can get pretty interesting. Well, you can use the data dictionary to keep track of homonyms and synonyms. Basically, don't use them. Try to make every idea have its own unique name. The problem you have is different users have different ideas of what things should be called, and different traditions of calling the same thing different things. So then you have to make it to make the users try to work out their differences, which is always interesting activity. But my thought is just avoid this stuff. Don't confuse yourself and your system. Well, here's the most important idea, right? We talked about the key and the foreign key, and the key foreign key idea makes a one-to-many relationship, right? We take the key of the one and we make it a foreign key on the side of the many, right? So one instance of customer has many instances of order. One instance of agent has many instances of customer, or serves many instances of customer. One instance to many instances. And that is the key relationship in all relational databases. And it's important to think that what we're talking about is an instance of one entity associated with many instances of another entity. Right? So that one instance is on the primary key side, and the many instances are on the foreign key side. Right? If you think about it, so here we have a agent code of 100, and here we have customer codes of 10,001, 10,002, 10,003, and each one of those has an agent code associated with it, 100, 100, 101. Right? So the one instance of agent identified by 100 had two instances of customer with the foreign key value of 100. That's why we call it a one-to-many relationship. We can also have one-to-one relationships, but they're relatively rare. And all it means is that the one instance in this entity is related to one instance in that entity, and it has to be implemented as a foreign key. All relationships and all relational databases are implemented through foreign keys. And so that's how even a one-to-one relationship is implemented. Well, a many-to-many relationship means that one instance of entity A is related to many instances of entity B, and one instance of entity B is related to many instances of entity A. Right? M to N, a many-to-many relationship. Well, in a relational database, many-to-many relationships cannot be implemented. They have to be what has to be done is a new relation has to be created, and there have to be two one-to-many relationships between the new relation and the older M to N related relations. And what we do is we create this bridge or composite entity that implements these many-to-many relationships and includes the primary keys of the two tables as foreign keys. So this composite or bridge entity really has foreign keys to all of the things that it's related to, and then each instance has a value to show which instance of the bridge relates which two instances of the other two entities. All right, so this is the bread and butter. One instance of painter paints one or many instances of painting. One instance of painting is painted by one and only one painter. Right? Does that make sense? A painter paints many paintings. Right? So we take the key of painter and make it a foreign key in painting. A painting is painted by one and only one painter. That makes sense. So if we store the value of the foreign key of the painter in painting, then we will be able to identify for every instance of painting the matching instance of painter. That is a one-to-many relationship where the primary key on the side of the one becomes a foreign key on the side of the many. And that's how they're implemented. All right, so we have a one-to-many relationship. Here we have our painter with our painter num as the key. Here we have a painting with painting num as the primary key, and painter num as the foreign key. All right, so painter has painter num, painter last name, painter first name, painter initial. Painting has painting num, painting title, and painter num. And painter num is a foreign key. Painting num is the primary key. Here in painter, the primary key is painter num. So whenever we have a foreign key, what we do is we store values of the primary key of some foreign or other relation or table. So what we have is painter num, and painter num is the foreign key, and what we've done is we've stored in it the value of a painter num from painter. And that value allows us to identify the instance of painter that is associated with this instance of painting. In other words, who painted this painting. And we can see here that we have, for one instance of painting, we have 1, 2, 3 instances of, or for one instance of painter, we have 3 instances of painting. Dawn Thunder, Vanilla Roses to Nowhere, and Hasty Exit. One instance to many instances. We take the primary key on the side of the one and we make it a foreign key on the side of the many. One instance of painter is related to many instances of painting. But one instance of painting is related to only one instance of painter. A one to many. Well, many to many relationships. As you become an experienced modeler, you can do these things in your ER diagrams, and that's what we're looking at here. We're looking at what an ER diagram. So we're trying to train relational modeling by ER diagramming when we haven't covered ER diagramming first. It's just a way of looking at the world, I guess. So here we have one instance of student has related to one or many instances of class, and one instance of class is related to one or many instances of student. Relationships always go both ways. There's always a meaning both ways in a relationship. So anytime you see this many-to-many relationship, right, one instance of student has many classes, one class has many students, you know you're going to have to break that down. And usually the thing that you put in between them, this association table, has some meaning, right? Here we're saying that a student enrolls in a class. So one instance of student has many enrolls, but each enroll is for one and only one student. Well, each class has many enrolls, but each roll is for one and only one class, right? So each instance of enroll has a student ID, Sorry about that. I can't even read that myself. So each enroll is going to have a student ID, and that student ID is going to be a foreign key, and it's also going to have a class ID. Whoops, that's an I, and that's a D, and that's underlined, so it's a foreign key. Right? So each instance of enroll can relate to one instance of student and one instance of class. Right? So that's what each instance of enroll tells us. It tells us that this student was registered in this class. Well, I thought I had some more data there to look at that with, but I guess not. So here's the sort of an expanded little model where we have one course has many classes, one class has many enrollees, and each student registers for many classes or many enrolls. Well, so here's an end-to-end relationship in our invoicing system, and this is a many-to-many relationship between invoice and product. One invoice buys many products. One product is purchased on many invoices. Right? So that's the many-to-many. What we do, and this is like one of the classic examples of all time for this idea of a composite or association table, is we create this new table, invoice line. And this is one of the classic ways of learning this concept of many-to-many. One invoice sells many products. One product is sold on many invoices. So we create this idea of invoice line that has a foreign key of invoice number, which each invoice line identifies one invoice that this line occurs on, and each invoice product code identifies one product that is sold on that line. And then we also know the number of units sold and the price. Now we can talk about why we store the price there on some other day, right? But this is the idea of many-to-many, right? Because we have one instance of invoice can have many products, and one instance of product can be sold on many invoices. So we create this thing called an invoice line, which is this composite or association table. And now in this case, it also has additional attributes, right? Line number and line units. Now, often it is the case with your association tables, your many-to-many, often there are other attributes. And whenever you see a many-to-many and you're looking to decompose it into a new entity and two one-to-manys, be aware that there's likely going to be more attributes than just the two primary keys. But those are the really important parts. Product code, right? Because one instance of product sells many invoice lines, and one instance of invoice has many invoice lines. One-to-one relationships are not that common. Here's a simple one. There's only one department head. So a professor chairs one and only one department. The department is chaired by one and only one professor. Now, where does the foreign key go, right? We have to have a foreign key to implement the relationship. Right? So let's think about it. We have the primary key of professor is, I'll call it PID. And I have the primary key of department, which I'll call DID. Right? So those are my primary keys. What should I do? I have to have a foreign key in one of these two relations. So what should I do? Should I make the primary key of professor be a foreign key in department? Or should I make the primary key of department a foreign key in professor? Well, in this case, I'd say there is a right answer. Sometimes in one-to-ones it's hard to pick. But in this case, it's not hard to pick. It should go in department, right? Because all the professors are not... If we put a foreign key... Well, let's start here. Well, so what we're going to do is we're going to put professor ID as a foreign key, dashed underline for foreign key, in department. Because every department will have a department head. So that foreign key, professor ID to department head, that value, the professor ID of the department head, will never be null in department, unless for some reason there's nobody department head right now. But if we put the department ID as a foreign key in professor, all the professors who weren't department heads would have null values for that attribute. Could we somehow make it work? Maybe we could, but my point is we would be wrong. We'd be wrong to do that. Well, indexing is all about improving performance. And believe me, performance is important. If your system doesn't perform, it won't matter how beautiful it is. People just won't want to use it. And so what we do is we use indexes to try to speed up access to the data. And this is a topic that we'll go into real detail in 5524 so that you really understand it. And so what we want to do is we want to make access to the data faster. And so what we do is we store the value for the key, and then we store how to find that value. Like, where is the reference point on the disk that's going to take us directly to that data? And that is what really makes things go fast. And these are all done by the optimizer. Well, like I say, we'll learn a lot more about indexing in 5524. For now, just know that you're probably going to have to make an index on every key and every primary key, and then you might make some indexes on some other attributes that if you're going to query on them a lot. But the idea is you have a key value, and then you have some kind of physical row pointer. Here they're just using rows as a conceptual thing to say that you're pointing to those rows in the table. Real indexes actually are going to places on the disk and have the pointer is not so simple as just to point to an actual row in a table. It's actually pointing to locations on the disk so that can be optimized. And it's you'll find I have an example when we get into performance issues, I think chapter 14 or who knows what, where we have in just a simple access database, you can see how much faster an index search is than a full table scan kind of thing. Well, then there's some basic rules defined by the inventors of relational database to say what is a database. Once after they come out with their ideas, there was people creating systems, and they weren't. These guys got a little bit tweaked, saying, "Hey, you got to have these things if you're going to be a real relational database." And so, I guess the things that I'm most hung up on are, you need physical data independence. That means your program never has to know anything about the disk, right? And you can change the way the disk is organized. You can change one disk for two, or whatever you do, and your program never changes, right? And then also logical independence, where the as long as you maintain your original data, then as you add additional attributes, then you don't ever have to change things. The rest of these are nice to have, but I don't think that dramatic. Well, so today we learned what is a relation and what are keys. We've learned that the most important thing is the primary key, and the way all relations and all relational databases are created is through the foreign key. We make relationships through keys and foreign keys that contain common values. Foreign keys contain values of primary keys that identify an instance in some other table. You already know something about relational modeling because you already know something about set theory. Your database life is about building a data structure with one-to-many relationships among these many relations to solve a problem. And then once we have designed our set of relations, and next week we'll talk about ER modeling, which is a tool that helps us to do that, then we can just create the tables in the database and start working. All right, well, that's all I have